Yeah, take that.
Okay, so our next speaker is Riccardo Gonzo, who's going to tell us about unexpected symmetries and unexpected integrability.
Yeah, thanks. Thanks for organizing put it together. Such a nice workshop. Really learning a lot. And also for allowing me to discover where King's College is, since I didn't know before. So I'm going to talk about symmetries, but from a classical perspective, so different to what has been discussed this morning, and in particular for Kerr black hole scattering. I think like one big motivation is we all know about these Scudder gravitational waves. Like now it's the 10th year anniversary, and we're really in an exceptional kind of situation where there is lots of new data coming, and it really requires to understand more the two-body problem in GR. I think also it's a very nice opportunity for different communities to come together. Before, like GR and energy physics community, they were really separated, and now really, I mean, people from gravitational self-field, you don't know what they are. It's just expansion of the mass ratio, the two-body problem. Post-Minkowski is what I'm going to talk about. It's just expansion in the coupling. Post-Newtonian is a slow velocity expansion. Numerical relativity is solving really on a grid on a computer like the two-body problem. I think this shows like this plot shows like there's really nice overlap between these techniques, between different kind of communities. The tools have been used, and there is lots more to be done in the future, like for the experimental purpose. For today, we'll just focus on the spiral phase where the black holes are very separated. And for this, we can model compact objects as point particles and really use high energy physics tools. So this is very important, and that's what I'm going to take into account today. Okay, so the idea is that we're a really simple dictionary. We have compact object of mass m. We take a point particle. We can add spin. I'm going to discuss about spin today. And we can also add tidal effects and GR correlator correction, some like higher dimensional operators, source absorption. And the idea is that why quantum field theory? I think like the nice part about quantum field theory, you get a very nice gauge invariant framework. I'm going to talk about on-shell techniques. That's something that doesn't appear usually in GR, because in GR, you work with coordinates, like sometimes like you work with Hamiltonians. Here, it's really, I'm talking about something really that allows you to rederive what is known in GR, like from point particles. Let me also thank the previous speaker for saying something nice about amplitudes. And I mean, I'm really going to talk about amplitudes today as well. And it also gives a new perspective. I'm going to try to say something more about it. So the idea is that you take two massive particles separated by same parameter. You try to scatter them. Okay, so you have initial state, these two massive particles, you scatter. I'm not going to talk about bound states, but there is a relation with that. I can mention that to whoever is interested, come to me. You let them scatter and they come out and they emit some gravitons. And of course, also the two massive particles coming out. So in this sense, you have like the out state completely determined by the in state and the S-metrics. And you can really understand the dynamics of evolution by taking an action. So GR minimally coupled with matter. And what we do, like in the post-Minkowskian expansion, is just expanding in the Newton in the coupling constant, so Newton constant. And this really gives a bunch of diagrams. And I mean, it's a very nice expansion, and you can really use tools for gauge theory developed like for understanding this. So to get quickly to a very important point, you also want to take some kind of classical limit. Okay, you want to understand like for example, where geodesics are coming from. I'm going to talk about that. So you want to really take some WKB approximation of quantum field theory. WKB approximation in this context, just like the Icona phase, is in this form. So you take the S-matrix operator and you exponentiate in terms of some n operator object. And what I'm going to claim about is this is really the semi-classical approximation. So what you do, you can expand your amplitude. You take some soft expansion. So all your massless momenta are scaled by h bar, and you expand in this soft region. Okay, and this is really where you capture the classical behavior. So what it does for you is resumming ladder type diagrams. So what you really want is, this kind of iteration ladder are kind of redundant. There's kind of iteration of this three-level potential, and this is made manifest by using this n operator matrix element. And to really get into contact with something that appears in GR, you want to do a Fourier transform and make contact with write that in hyperparameter space. Why? Because the results in GR usually written in terms of, for example, angular momentum. Angular momentum is related to the hyperparameter, so you really want to do the Fourier transform. And also it allows you to exponentiate these diagrams. So the result is that the S-matrix just becomes the Icona phase in the conservative regime I'm going to talk about today. And in particular, it's also related to what is called radial action. So the integral of the radial momenta, you can think about that just going to the central mass frame, okay? You have only dynamics on a plane, there are spinless particles. And so there is only one really important degrees of freedom, which is the radial kind of projection of the relative momentum. So you can integrate that between some turning points, and this actually turns out to be related to the amplitude directly. So you provide a connection between what something that's computed in GR as something that's computed with amplitudes. And I'm going to use it now for making some claims about scattering of Kerr black holes. Let me also make contact with the uniformalism, which was touched upon in the previous talk. So if you think about this exponentiated form here, right, you can just think about the variation expectation value operator. So you write down the exponential representation of this, you use the Baker-Campbell-Hausdorff formula, and it allows you to get some iterator of commutators, okay? So there is a nice way of thinking about how classical physics works. If you think about this iteration of commutators, it reminds like an iteration of what you get in Hamiltonian flow, right? So, and that's exactly what we're after. So if you consider two-body observables a function of the external kinematics, remember we want to get something on shell, okay? Not gauge dependent, completely on shell. It kind of calls for a mapping between commutators and Poisson brackets, or more precisely, Dirac brackets, because here we have a system with constraints. As you know, I mean, this is just kind of some dequantization of what is a quantum picture. But this part will really be new. So it's something that's not been never done in GR before. And to understand this, we go back to the word line. So if you think about the two scatter of two black holes, you get just some straight line trajectories, okay? And their algebra is just the B, so the impact parameter of each black hole, and the velocity, their Poisson brackets is just eta mu nu. So it's different than what you use in Hamiltonian, because Hamiltonian usually have X and P. X is gauge dependent. Here I'm pushing it to infinity, minus infinity, so it becomes B. That's related to impact parameter, to the angular momentum, so it becomes something on shell and gauge dependent. And this is very important. So it's something that it allows you to use on shell tools to derive statements about the scattering on Kerr black holes and many other kind of things. So you can to understand, like from this algebra, okay, this is just Lorentz algebra. This is just the Poisson brackets, just standard point particle mechanics. You need also to impose some condition when you have spin. One is the spin supplementary condition. Then you have on shell and transversality. So when you do that, transversality also means, the particle moving on a plane. It comes from this Fourier transform here. This one, you have some delta functions, just telling you that the two black holes are on a plane. And once you do that, you derive some Dirac brackets. And this one's like really tells you how basically the system evolves from the initial condition to the final condition. So, so how can, and this also makes contact with some old results on Anson Regge on the relativistic spherical top from a kind of on-shell perspective. As I said, there is no X and P, it's B. So B is a gauge invariant object. Okay, so what are you gonna do? So we're gonna try to compute like this object K now with a particular model and particular probe limit in Kerr, just as an example. So take this action, it's just a word line action, okay? And there are some constraints here. So if you add spin, you can add some spinners. There is some Hamiltonian constraint, charge constraint. In particular, we're gonna care about the on-shell constraint, so the particles that are living on shell. For the case of a spinning particle moving in Kerr spacetime, so it's a very simple problem. It's an integrable problem. It's very remarkable for a spinless particle, a test particle, and also for a spinning particle as some order in a spin expansion, particularly linear spin. So it's an interesting problem from the integrability perspective, okay? So in this case, you take this Hamiltonian constraint, okay? It's just the on-shell condition. There is your momenta, covariant momenta, and then you have some curvature corrections. And you see, if you're able to fix the radial momenta, the one I was talking about before, the radial momentum in the center of mass plane, in terms of the other quantities, you basically have, solve the problem. I'll show that is possible. There are here some symmetries. So one is conservation, of course, of the mass. One is conservation of the energy, the angular momentum. But famously, there are also tensor symmetries. Okay, so the Killian tensor is conserved on a Kerr black hole. And when you contract that, you can write this case. So these are related to, Carter constant, and also there is an extension, the Rudiger constant. It doesn't matter what they are the space size symmetries of the Kerr black hole that basically appears like in this on-shell constraint. So, okay, so then now you can solve this constraint. So these are pi aggregated in terms of P. You write PR. So it's completely determined by the external conserved quantities. And okay, there is some nice relation with the way that this simplifies the spin connection. I just want to say that there are interesting also classical problems that are integrable. And now we're going to work with this, so you can integrate it. Expression is horrible, okay, some hypergeometric function. You also need to regularize because if you do scattering, there is infinite divergences right far away, so you also need to regularize. And these are explicit expression, okay, in terms of the roots of the potential. The nice thing I want to say is that this connects also with the, what I was talking about, the amplitudes in the WKB expansion, this object here. So it's not true that amplitude are only perturbative. This is a resummation in classical physics. It's all order in G. So it's also something I want to stress. It's not always true that it's an asymptotic expansion. This example is not the case. So, right. So, some higher regulator is needed. Okay. Doesn't matter the expression, there are many others. But the point is that now we have a formula, right? So from the init formalism, let me also stress something I want to connect with the previous talk, since there's a nice paper by Weinberg 20 years ago on cosmology doing incorrelator and using interaction Hamiltonian and write it down exactly in expansion like this. Just want to emphasize this, very nice. But yeah, anyway, once you turn commutators into Dirac brackets, now you get an iteration. And now it's where you actually have something powerful. Now it's where like you start to use really on-shell tools like to compute observables, in particular variation of velocity and spin vectors, okay? Because you put your algebra, so the velocity and spin vector, you just iterate the brackets are derivatives, okay? And you put on a code, and this is very fast. And we have used this like so we have developed this framework, and we've used it to compute like various observables from the scattering radial action that you can extract from amplitude. So by doing the procedure I was talking about before, you can just extract the radial action also from worldline. There are various results of various order in PM. So we have collect all of them, and now we're going to make statements about symmetries. Okay, so we collect all the statements from using like particle physics tools, and now we're going to make new claims about symmetries using this structure. So yeah, the question is, can we find any structure? And so the natural thing to do, right? So you have think about Hamilton equation motion, like in Hamiltonian. You just have derivative of your operator over time, right? That's equal to the bracket of the Hamiltonian with your operator. That's natural in classical mechanics. So now you have the same. So our answer is that if a quantity is conserved, then the Dirac bracket is 0 with the charge. So we impose this, okay? Notice again, it's an on-shell constraint because Q is on-shell, IR is on-shell, and the brackets are also on-shell engaging variant. So nothing relies on the Poisson structure because it's pushed to infinity now. So it's a completely on-shell statement. And this now we're going to try to make some claims about when this system is integrable, okay? So to get an integrable system like in the uveal kind of form, you want like n charges in evolution in a two n-dimensional phase space. So what you can do, you take your kinematics, okay, your initial kinematics. You go the reduced phase space is the one on a plane, in particular the input parameter. So input parameter, I introduce it here, right? Yeah, here. That's the distance between the two. This can be put on a plane, okay? So it's a two-dimensional degrees of freedom. Yeah, so then you have the relative velocity between the two velocities. Again, you can figure out that in central mass frame, and then some projection of the spin vector. That's also two-dimensional. So in total, basically, you need 4 charges because it is an 8-dimensional phase space, and we define some notion of asymptotic integrability, which is not as strong as the standard UV integrability because that also works for things in the bulk. Here we have expanded things at infinity, but it's a kind of weaker notion. we ask these charges to be in evolution with each other. So now the natural question, what are these charges, right? So I was talking about the Killing vector and tensor symmetries of Kerr spacetime that, for example, the time translation, angular momentum rotations, and then, as I said, like the Killing out tensor, like in, so these are natural symmetries. Yeah, so then you can use those. You can find some nice expansion of these conserved charges at infinity. So you send R to infinity, you make contact with the kinematics at infinity, you have explicit expressions. So these are, again, look at that, they're only function of the kinematics at infinity. So they're never, usually when you write them down, they are in position space, there is some X. Here they're pushed to infinity, so then you make contact with something really, that's the gauge invariant on shell. For the year we use like the quadratic spin correction to Carter constant, something very new, was discovered just I think 3 or 4 years ago by these people. So it's something that before it was not even understood that it was concerned, and now we have an expression also in this formalism. And now we can just test, right? So this is the condition that we have on the top, and we can just test it, okay? And this is what we found. So we take this L, Qy, and Q, okay, and we check in the probe limit first, because the probe limit, as we said, like there is some nice background symmetries, and we see that actually up to spin to the 4, so this is only the available data, there is a conservation, okay? We can only test perturbative, but we have results up to 5 p.m. G to the 5. It breaks down as spin to the 5, but up to spin to the 4 is conserved. This is new. Why? Because I mean the conservation was established up to quadratic in spin order. Here you see S2 square, S1, S2. You don't have spin cube terms. So you might expect this breaks down as spin cube, but it doesn't. And that's one of our new results that was not known in GR. Of course, this relies on this expansion of infinity, as I was saying. So it's a weaker notion, and one has to establish what is the implication for bound orbits. So it is an important problem because most of the expansion nowadays, for example, gravitational surface relies on action angle variables, and it relies on any interval system like as a background system. So really to do perturbation action angle variables to study waveforms for particles in Kerr, you need to understand like if the problem is interval, what are the action angle variables for that? We also study beyond the probe limit. So integrability is actually broken, maybe not unexpected, beyond the probe limit, unless one black hole is spinless at 2 p.m. So we also studied this result at low G order, and it's also broken for non-minimal couplings. It's expected if you have a neutron star, so you have quadrupole correction to that, so a spin square term that appears, then it's broken again because you don't have like the nice symmetries. The Killing Yano tensor only appears when you have Kerr. So Kerr is very related to point particle corrections. There might be an notion of perturbative integrability where you add G corrections to these charges. We have explored a bit that, but it's still unclear whether it makes sense. Just my comment is that on-shell tools provide a new path forward to understand the conservation load in this scenario. So to advertise, I think that there's lots of new developments, application particle physics tools to gravitational waves, relatively new, like we have lots to explore. The important part that has become more and more important is to study the phase space of classical dynamics, which means really like think about what are the symmetries of exact approximate solution of the Einstein equation. Use something like the radial action. I was talking about Hamiltonian. Hamiltonian is off shell. You can do various gauge transformation, but to check things really to have some nice on-shell framework, you want something like radial action in these extensions. This is very important for effective one-body other applications. Dirac is one example. I haven't talked about today scattered bond maps. It's one of my favorite topics, but not today. And there are ways to connect what I said about with the bound case. Okay, so it's also important to explore this, and that's related to the phase space because the radial action is what analytica continues actually. I think it's interesting to study also non-space-time symmetries. There's something new that has been explored in the past 5 years. That's spin shift symmetry. Some symmetry of the 4-point spinning amplitude in the Icona regime, where you shift the spin vector by something proportional to the momentum transfer. And we also studied that in this work. Also the bootstrap of spinning dynamics from the aligned spin. So in general, you have precession when you have generic spin, right? Because they're not aligned with each other. So you can have 3D dynamics. But it's interesting when there is integrability, you can actually bootstrap the radial action from the aligned spin. So it seems like these symmetries are very powerful when they are there. And it's also a very interesting topic for the future, I think. But just close and say, like, resonation perturbative methods is also needed. So I discussed about amplitude, but I also saw explicitly an example of something with some in G. That's possible because in classical physics, you can solve differential equations. And I think it's an exciting direction for the future to make contact in the future. Thank you.
Thanks for the nice talk. Just making sure I understood everything. So this integrability arises only in the conservative regime?
Yeah, we only store in the conservative regime. Yeah.
And
it's expected to be broken when you add dissipation.
Okay, expected, but like...
Yeah, you can extend, so I haven't discussed this, but we have a way to extend this exponentiation argument and the brackets to radiation that we've done recently.
Yeah.
And with that, you can study what's the deviation from the conservation law. And that's actually something that has been done. So 20 years ago, when they started doing the Salford's expansion, people start studying how the fluxes modify the conservation law. So they start with the probe limit, they go to action angle variables, and they say, oh, then the variation of the energy, the variation of angular momentum, the variation of the Carter constant is equal to some flux in time. So you can try to study this also in this scenario. Yeah, we don't have the time because the time is integrated out. It's not gauge. Yes. So it's all on shell and gauge invariant. But we expect it anyway to be broken in integrability. But the way it's broken, it's also interesting because it tells you exactly which kind of force is there, like to change like the integrable motion. So we also know to construct that in principle. Yeah.
Okay, perfect. Thanks.
Unfortunately, only for scattering so far. But,
yeah, I just wanted to know what is the state of the art, like from directly going from amplitudes to the waveforms, if you can say something.
Sure. And so for amplitudes, the waveform, so it depends exactly which method you're using to go into amplitude the waveform. Right now, it has only been implemented like in effective one body. So the way it's done, you take the amplitude I was describing or the radial action. You convert that into a scattering angle that you can match with effective one body theory. So there is an Hamiltonian in the effective one body. You match that Hamiltonian on shell. And so they have used, for that, they've used up to 5 p.m. 1SF data so far. So it's a G to the 5, and then first order in mass ratio. There's also correction second order. So there they've corrected only the Hamiltonian, and then they've run the equation of motion. So what they do in the effective one body, they have the equation of motion that comes from the Hamiltonian, and they have the fluxes, and they've only corrected the Hamiltonian, and then they get some waveforms out. These waveforms do show some improvement, but it's almost, it's mostly for eccentric binaries. Of course, these are hyperbolic motion, so that it performs very well for eccentric binary, which is great because post-Newtonian works well for near circular binaries. So exactly the complementary regime. So if it's not the type of sources we'll see now, but for Lisa sources, we really expect a lot of eccentric binaries. And for that, like these kind of methods can be applied more. Also, like for dynamical capture events and things like that. So it's something that at the moment is not used, but because the type of sources are different, now we have equal mass systems, almost equal mass system. We really need a different frequency band to capture like eccentric events. And so when that will be accessed, then you can try to rely more on these methods. But they are, the state of art is implementation into something like EOP. Otherwise, people compute scattering waveforms, and the state of art is one loop, G to the cube. But that's a scattering waveform, not a bound. No problem.
Any questions?
Could you explain what a scatter bound map is? I'm not familiar.
Yeah, sure. Well, Do I have a slide for something? Well, you want maybe the last one is closer. So it's I'm talking about scattering right here. So hyperbolic type of motion. When you bring like so you then consider the energy minus the total mass. Okay, that function is positive for scattering and negative for bound. So you can think that there is some analytic continuation. The reason why it's true in classical physics, actually, in quantum physics is much more complicated. But in classical physics, because you have differential equations. So if you have a differential equation with an Hamiltonian, the only thing to change between scattering and bound are the boundary condition. So if you have a way to relate the boundary condition, which you can, there is a way to kind of analytically continuing the energy. The result like this, the radial action. So one example is directly this one, right? So this one, it's complicated, okay? But these roots are a function of the energy. For example, all these charges, a function of the energy. There is a map between this scattering reaction and the boundary reaction directly. And the boundary reaction will be boundary reaction over an orbit, average over an orbit. That's what you get. And you need to analytically continue in the energy, essentially. So that's what you expect. Just like the Hamiltonian, you bring the energy from above threshold to below threshold, you need to continue. If you have the analytic expression, you can do it. Of course, numerically is another story. But that's why analytic expression are interesting here, because you can try to leverage on the analytic properties and try to analytically continue. But there is a lot of discussion. But if you're interested, I can tell you more. But thank you.
The relations between the conserved quantities went by a little fast for me. So
yeah,
if you go back to your Q and QY,
this one?
Yeah.
Yeah.
So which of these is related to the Killiano tensor, and what is the other one?
Yeah. So these are these two. There are two related to the Killiano tensor. So it's contracted with different things.
Okay.
So Q is the generation of the Carter constant. This is the quadrupolar correction of Carter constant. And QI is called Rudiger constant. And they are both related to the Killiano conservation. Yeah. I just find it interesting that the scarce integrability is also there in a different form, like in other problems. So I thought, yeah.